Alrighty, last section. I just want to address some problem solving strategy because I realize a lot of times, like I mentioned at the top of this lecture, I leave you with just all the theory and all the equations, but I don't really demonstrate how to solve any of these problems. And so, taking some of that feedback, I'm going to try to just go over a problem here that I think is sets you up really well to solve the rest of these problems, right? So you have all these equations, which are going to be on an equation sheet. So they're not going to be too mystifying, and you know how to do algebra, but it's still nice to be able to kind of go through a problem and know how to set it up and know what they're asking for. So let's read through this, and then let's do an example problem that I mentioned before. So, by the way, these boxes here are in university physics, and they exist for every new class of problems that we go over. And so if you ever are just wanting just general strategy for how do I do this type of problem, I don't even know how to approach it, go ahead and just go look in that PDF and see how they recommend you approach that problem type, because these are very useful. So first, you got to identify the relevant concepts. So there's another problem-solving strategy for mirrors, which they have. It applies equally for thin lenses here. But here we're going to be using image formation by lenses using both principal ray diagrams and equations. So same thing as mirrors. So you're going to have a geometric kind of approach to solve these problems. And you're also going to have like an equation type approach that you can go with to solve these problems. And both can get you there, but and sometimes both are certainly needed. But for the drawing one, sometimes it's really involves you drawing a very precise image, which takes a lot of time. So, but it's at least nice to have a good sketch. So they say, set up the problem by identifying the target variables. What are you trying to solve for? Execute the solution in the following steps. So they recommend that you draw a large principal ray diagram. If you have enough information, use graph paper or quadrilateral ruled paper. Orient your diagram so the incoming rays go from left to right. Draw the rays with a ruler and measure distances carefully. I probably would not opt for that every time, but sometimes it's possible that that would be the best way to do the problem. But that takes a lot of time, so I would recommend using a sketch to get an idea of what's going on, but relying on the equations to solve the problems when possible. So they say draw the principal rays so that they change direction at the midplane of the lens, right? For thin lenses, you just ignore the fact that there's a left and a right and a distance between, so just that midplane. For a lens, there are only 3 principal rays compared to 4 for a mirror that we talked about before. So you're going to draw all 3 whenever possible, and the intersection of any 2 rays determines the image location, but the third ray should pass through the same point. So it's a good way to check and see. Like before, I wasn't drawing a very good diagram when I realized that my third ray did not pass through the same point. So if you're trying to go based off a diagram approach and measuring the actual line solution, you can, because this is geometry. Geometric based, but you have to be careful. If the outgoing principal rays diverge, extend them backward to find the virtual image point on the incoming side of the lens. And we've seen a couple examples of something close to that. And then you're going to solve the equations. So this equations that they reference, that's just the image object radius of curvature relations. The thin lens equation, in other words, and the magnification and all the other equations that we've come to depending on the case, right? And you're going to solve them for the target variables. So the image from the first lens or mirror may serve as the object for a second lens or mirror. We kind of saw something like that when we derived the lens maker equation. In finding the object and image distances for the intermediate image, be sure you include the distance between the 2 elements, lenses and or mirrors, correctly. And then, as always, evaluate your answer. So make sure that at the end of all this, you're checking your answer and making sure it all makes sense. Don't just chug and plug and then write down some crazy answer that you haven't thought about. And it definitely takes a brain to think about, okay, what does the magnification mean, right? What is what does this mean if it's a virtual image or a real image? There might be questions asking that if a camera was at that point, would it be able to form an image or capture the image? If it's a virtual image, then you can't put the camera there. There's no physical rays coming into the optics of the camera. So there you go. Definitely lean on this stuff, these little boxes. It will help you. And we're going to go over this problem here. Expand this. An image of an image. All right, so let me block out a couple things that we're going to find out. So bear with me here. We don't need to know that yet, and we don't need to know either of these yet. So you saw nothing. You saw nothing. Okay. So let's read through this. So converging lenses A and B of focal lengths 8 centimeters and 6 centimeters respectively are placed 36 centimeters apart. Both lenses have the same optic axis. An object 8 centimeters high is placed 12 centimeters to the left of lens A, right? So I gave you, I have to use a different, more striking, I'll use red here, more striking color. So this distance, and they gave you that it's 8 centimeters high, right? They give you that height. Find the position, size, and orientation of the image produced by the lenses in comparison. In combination, rather. So such combinations are used, they tell you, in telescopes and microscopes, and those kinds of applications are discussed. If you want to read about all those things, there's like a whole 1/3 of this chapter in this textbook that talks all about applications. And I think in fundamentals also they talk about lots of applications. I like to stick to just the basic stuff and let the problems kind of expand all the applications for you. So how do we do this? So following the same problem-solving strategy, we're going to identify and set it up. So we got this drawing that this example has done for us, but this is something that you would draw for yourself. So the object, O, right, lies outside the first focal point, F1, of lens A, which therefore produces a real image, I. The light rays that strike lens B diverge from this real image just as if I was a material object. Image I, down here, therefore acts as an object for lens B. Our goal is to determine the properties of the image I prime made by lens B. We use both ray diagram and computational methods to do this. So, execute. We have drawn the principal rays 1, 2, and 3, right? 1, 2, and 3 from the head of the object arrow O to find the position of the image I made by lens A. And then we've drawn principal rays I prime, or 1 prime, 2 prime, and 3 prime from the head of I to find the position of image I prime made by lens B. And I want you to pause here and think about this. Given everything that they've drawn, right, how in the world would this ray here and this ray here, how would that actually be a physical ray? So we have this object here, yes, but it's not a real object. It's one of those weird funky image objects, right? And so it's just like a midway point for the light. And so yes, here there is a clear image of the tip of the arrow, even though it's magnified. It's a clear image made by that lens A. And so if you were to, put your eyeball there, you'd be able to see it clearly. But the path of the light is not done, they're saying. We're considering it if it keeps going on through lens B. Well, there's no mirror here that's causing the light to reflect. So this green ray actually would not do that, right? So there isn't actually a physical ray that's coming here, even though we're considering a principal ray coming from there. And usually we're allowed to do that because we say, well, there's light emanating from everything, right? So if you have, a nice little fishy, you have a sun up here, then it's hitting all points of the fish, and then it's scattering and hitting, reflecting in all directions from every point on the fish. And so we can consider any ray coming from any point on that fish. But in this case, we can't really do that. We can't say that, oh yeah, there would be a physical ray there coming from the object. We have to go back into this whole consider rays that don't physically exist or weird space. So there's no reason why we can't consider a principal ray and what it would do if this were a real object that were self-luminous or reflecting this way. But it's also important to understand that there isn't a physical ray 2' or 3'. We can still consider it, but that doesn't mean that they exist. This bottom one, however, this orange ray that comes, the third principal ray would come straight across, go right through this point and continue on. So 1' does exist because the light doesn't do anything here, it just keeps going. So it would actually end up there, right? So now the next logical thing to think about is, how is this image formed then? Well, it's formed just by that bottom ray. So it's going to be very, very dim. This first image is going to be very bright because any light coming in from any angle is all, right, they're all going to converge at this point here. But only some of those rays that make it to form this image are going to keep going. It's only the ones that are coming straight through and going on and forming this image here. It's not all of them. And so it might not be as bright, but it will still form an image. All right, so I thought that was interesting to cover. I think it's a really interesting consequence of geometric optics that some may not realize, that you have to get comfortable going into this non-physical space for maybe a portion of finding a solution, just so that you can arrive at a real solution, so you can see what the real, or I guess virtual image, but what it really is doing. There is this kind of like weird in-between sometimes, this weird interstage where you're not really talking about physical things, or you're considering things that aren't physical. But that doesn't end with geometric optics. So if you're going on in physics, going on in engineering, especially electrical engineering and other things, there's lots of things that you have to get comfortable with not exactly existing for midpoints during finding a solution. So if you take quantum, this is the case. If you go on to graduate level electricity magnetism, so graduate level physics 2, that would be the case. You get complex, anyways. So when you get to those places and those classes, you won't be intimidated like other students and say, this doesn't even exist. What are we talking about? You will think, well, my instructor Joel told me way back in geometric optics to not be feared by a non-existing intermediary step. Just continue if the mathematics makes sense, and you may arrive at something real and useful. That's the truth. All right, so that was a big rant, but hopefully you found it interesting. So we're going to sketch and identify the equations. So we've sketched, or they have sketched for us, and the equations, identify equations. We're going to use the thin lens equation. 1 over s plus 1 over s prime is equal to 1 over the focal length. We're going to use the magnification equation for a thin lens, which is negative y prime over y, right? And that's, it's supposed to be s prime over s. And so for lens A and B, we're going to get two different things, right? So for lens A, we have the object distance being or not the object distance, that was right, y prime over y. And so we have y prime being that, and then O being the object height. All right, let me say this better. So magnification from lens A is equal to negative I over O, right? And magnification of B is equal to I prime, negative I prime, over I. So there it is. All right, so those are the equations that we have to work with. So now let's split it up and do the first part, the first event at lens A, and then the second event at lens B, similar to our lens maker equation derivation. But this time we're not doing any kind of weird pretend the surface doesn't exist. We just have two different lenses, so it's a little bit more straightforward. So lens A, first what happens is we're going to use our thin lens equation, 1 over 12 plus 1 over S prime is equal to 1 over the focal length, which is 8. And so, if you have trouble doing this kind of stuff in your head real fast like I do, you can write this out and find common denominator, and that tells us that S prime is equal to a positive 24 centimeters. All right, so we're going to need that. And then the magnification at A is equal to negative 24 over 12, which is negative 2 magnification. And we did that because similar triangles. So hopefully you can follow along there. So what does this mean for image 1, this image I here? So that means that the first image, image I, is, because of this negative sign, inverted. Because of this 2 here, it's twice as tall as the object. And because of this image distance here, and lies 24.0 centimeters to the right of lens A. Okay, so now we're ready. We have our dimensions. We figured this one out. Now we can proceed to the second one. Okay, so now we have our lens B event, lens B. So if A and B are 36 centimeters apart, then 36 minus 24 is 12, right? So A and B are 36 centimeters apart. That means 36 minus our image distance from before, which is 24 centimeters, is equal to 12 centimeters for our new object distance. So that means that, right? So now we can go back to our thin lens equation for this lens B situation. 1 over 12 plus 1 over S prime is equal to 1 over the focal length of lens B, which is 6. And yet again, common denominator here. Boom. I always have to write those out. S prime equals a positive 12.0 centimeters. And that is our answer, one of the things that they're looking for. And if we do the magnification of B, then we find that we get negative 12 over 12. And so what this means is not that the final image is 1 times the original object and inverted, because this is in reference to from how it came to it. So it's referencing this guy here, this intermediate image, and this final image. So from that intermediary image, we have inverted and not magnified at all, which is about what we see in this drawing here. Here we go. So from this guy to this guy, it's inverted, but it has not changed height, right? And so it's still twice as tall as the original object, and it inverted twice, so it's erect in the end, right? So that is the solution of what we were looking for here. That's an image of an image. There you go. So the rest of these types of problems follow just like that. You have your equations. You have to determine which equation applies to what you're talking about. Is it a thin lens? Is it just a curved spherical concave mirror? Is it a convex refractive surface, not a thin lens? What's going on? So you can have kind of complex optical systems, and it's actually kind of fun to trace through and see how they work and see what the final image is like that's formed. And you get to see how telescopes and cameras and our human eye and all these different kinds of things work if you work through some of these problems. So I encourage you to do that. You now have all the tools for geometric optics. This ends our tour through geometric optics and using the ray model of light. And so you should be able to solve all problems of this type. There's no more information coming. Next lectures, and for the rest of the class, we're going to pick up with physical optics, and we're going to talk about the wave model of light, and we're going to talk about interference and diffraction and all the things that come along with a physical wave model of light. Alrighty, that's it for today.